Is it Thanksgiving? After next week? No, that's a week before, right? So we should have our second exam before Thanksgiving, so that we can enjoy our Thanksgiving, right? Oh, Tuesday on the week of Thanksgiving?
No.
That's your suggestion, right?
I say I like the players.
So let's talk about the heat equation that we studied in, the chapter 2. So the heat equation was partial over partial x of k times partial t over partial x plus partial over partial y, k times partial t over partial y, and now z direction, partial over partial z, k times partial t over partial z. Am I recording this one? Plus heat generation, q dot, is going to be the time dependent term, which is density times specific heat, partial temperature over partial time. So in this case, we are going to study one-dimensional, which means we can neglect y direction and z direction. Steady state, we can neglect the right-hand side. Conduction heat transfer with heat generation. So this is going to be the heat generation, and this is going to be the conduction term. So now we don't have y, z, and time t. So we can convert this one back to ordinary differential equation, which is d over dx, k times dt over dx is going to be minus q dot. And now we can assume that thermal conductivity K is constant. Then this one comes out, and then we can divide by thermal conductivity K. Then the equation that we are going to solve is going to be dt square over dx square is going to be minus q dot over K. So this is the equation that we are going to study. Then how can you solve this equation? It's very simple. It's a second order ordinary differential equation. So you just need to integrate twice with respect to x. Then what do you get? If you integrate with respect to x, you will get dt over dx is going to be minus q dot over k x plus a constant c1. If you integrate one more time with respect to x, you get t is going to be minus q dot over 2 times k x squared plus c1 x plus c2. So this is the general solution for this, the heat transfer problem. One-dimensional, steady state heat conduction with heat generation. So if you compare the previous, the heat equation, one-dimensional steady state without heat generation, if you get rid of this q dot, then the temperature, the equation is going to be exactly the same as the heat equation for one-dimensional steady state heat conduction. Then we are going to study this temperature equation on a simple domain. In this case, when we have a plane wall. And let's say, our x direction starts from the center of this plane. So this is x direction. So that means that this is minus x direction. And then the temperature distribution within this plane wall, because of this second order, because this x squared, it's going to look like this, right? The parabolic shape. So, and depending on the temperature and its location, so let's say that this one is going to be minus TA at the surface, and this is going to be, this one is going to be TS number 1. Let's say this one is TS number 2. Then we have two boundary conditions. One is going to be when x and we have two boundary conditions. One is going to be, if you say the thickness of this plane wall is going to be 2 times L, so this is L, and one boundary condition is going to be when X is L, temperature T is going to be TS2. When X is minus L, temperature T is going to be TS1. So if you apply these two boundary conditions into this temperature equation, then you can determine the unknown C1 and C2. And then you can determine the unknown C1 and C2, and this is the temperature distribution within this plane wall. Okay? Then what about if you have some unique case, such as plane wall with symmetric boundary condition? So we assume that the temperature of the surface in either surface, we have the same temperature, Ts and Ts. And then what is going to be the temperature distribution in this example? Then we can start from the same equation, which is right here, this equation. So the heat equation for this symmetric boundary condition is going to be so the differential form is going to be dt square over dx square is going to be minus, what's it, minus q dot over k. So to solve this equation, you can integrate twice, right? So if you integrate twice, you get dt over dx is going to be minus q dot over k x plus a constant c1, and you can integrate one more time, then temperature T is going to be minus q dot over 2 times k x squared plus c1 x plus c2. So this is the temperature distribution. Now we have unknown c1 and c2. So we assume that we have a symmetric boundary condition, which means we have a plane wall and there's a heat generation within this plane wall for the amount of q dot. Because of this q dot, as you can see, the temperature distribution is going to be this shape. Then we assume that the temperature at each surface is going to be the same temperature, Ts, and the thickness of this plane wall is going to be 2 times L. So each side is going to be has a thickness L. So the total thickness of the plane wall is going to be 2 times L. Then we can come up with two boundary conditions. The first one is temperature T is going to be Ts when X is L. And the other boundary condition is this one. Temperature T is going to be, again, the same Ts when X is going to be minus L. So if you apply these two boundary conditions on this temperature equation to determine unknown C1 and C2, then the general solution is going to look like this one. This one. Temperature T is going to be Q dot over 2 times K times L square. L is, by the way, the half of the thickness, times 1 minus X square over L square plus TS. Then this equation can be very useful because of this symmetric condition. If you look at the center line, what is the temperature difference right, left of this center line and right, the right of the center line? So this location, this position, and this position. Let's say this one is T1, this one is T2. So we have this point and this point. Then, because of this symmetric boundary condition, we can say T1 is the same as T2, right? Then, what is the temperature, what is the heat transfer between T1 and T2? When T1 equals T2, what is the heat transfer between T1 and T2? According to the second law of thermodynamics, heat transfers from a higher temperature point to a lower temperature point. If T1 is the same as T2, there should be no heat transfer across this center line. Make sense? So in this problem, there is no heat transfer either way crossing this center line. So that's not possible. Then what is the case when we have no heat transfer on this surface? When we have an insulation. So this symmetric boundary condition can be used as a plain wall whose thickness is only half of this one. So just add, if we assume that the left-hand side is insulated, so if you add an insulation, then if you add an insulation, so one side is insulated and the other side is open to a surrounding fluid, and when there's a heat generation, Q dot, then the temperature distribution should be exactly the same as this symmetric boundary condition. So right half of this temperature distribution should be the same as this one when you have an insulation. Because when you have an insulation, that means there is no heat transfer. So when you have a symmetric boundary condition, that guarantees that there is no heat transfer across this center line. So this problem is exactly the same as this problem in terms of heat transfer. So when you add an insulation and when there is a heat transfer and when there is a heat generation, the temperature distribution is going to be exactly like this one. And this temperature distribution function is going to be here. T is Q dot over 2 times K L square 1 minus X square over L square plus TS. Then when you have a heat transfer problem like that, what is your point of interest? When we have the lowest temperature and when we have the highest temperature. So at what point should have the highest temperature? On the surface where insulated. So this point should be the highest temperature. Then we are going to say this point, the highest temperature is going to be T0, and we have the lowest temperature. This is the surface which is exposed to the fluid surrounding it. So we are going to say Ts, the surface temperature, and T0, because if we assume that X direction is this way, this is the point when X is 0. Because this is the condition of this symmetric boundary condition. X starts from the center line positive x, negative x. So similarly, this is when x is 0. Then, can you determine t0? Yes, from this equation. How? By substituting, by adding 0 for this x. So this x is going to be 0. Then what is t0? T0 is going to be q dot times L squared divided by 2 times k plus ts. So when we have a plain wall and one side is insulated, the temperature difference between the highest temperature point and the lowest temperature point can be determined by this equation. Then let's talk about one more problem. Okay, I get that. We now have an equation to determine the temperature difference between the highest temperature point and the lowest temperature point in this plane wall when one side is insulated. And there's a heat generation, Q dot. This is the volumetric heat generation, so the unit is going to be watt per cubic meter. So if you want to determine the exact rate of heat transfer, then you need to multiply by the total volume of this plane wall and this Q dot. That will give you this much heat rate is going to be generated in this plane wall. Then, if you assume that this is a steady state heat conduction problem, what it makes steady state heat conduction, we should have constant temperature T0, constant surface temperature Ts. So this T0 and Ts should be constant. Then it is a steady state. What about the temperature goes up or down? Then that's a transient heat conduction problem that we can study in chapter 5. So let's assume that we have a steady state heat transfer problem. Since there's a heat generation, we need to get rid of this heat. Otherwise, the temperatures of this plane wall is going to increase. Then how can we remove this heat from this wall? This way? No, it's not possible because the left-hand side is insulated. The only heat transfer direction is going to be to the right-hand side. Then this is the surface of this plane wall. And what is on the right-hand side? Fluid. So what is the heat transfer between a surface and fluid? Convection. So there's a convection heat transfer from the surface to the surroundings. And the temperature of the surrounding is going to be T infinite. Then what kind of heat transfer in this direction? Q by convection. Do you know how to determine convection heat transfer? We studied from chapter 1. We can use Newton's law of cooling that can be determined by H, convection heat transfer coefficient, times surface area where heat is transferring through, times temperature difference. Okay, then whatever heat generated in the plane wall should be removed from the plane wall by convection. Otherwise, the temperature is not going to remain constant. So to maintain constant T0, constant Ts, the entire heat generated in the plane wall should be removed. Then what is the heat generation? This Q dot times the entire volume should be the same as Q by convection. So how do you determine convection? H times A times delta T. Then let's look at this equation. How do you determine this volume? The volume can be determined by the surface area where convection heat transfer takes place and the thickness of this wall. What is the thickness of the wall? L. So this volume can be determined by area times the thickness, L. And what about this delta T? That is the temperature difference between the surface and the surrounding fluid. So delta T should be Ts minus T infinite. So this one is going to be Ts minus T infinite. Then we have area, so we can cross them out. Then the equation is going to be Q dot times L is going to be H times Ts minus T infinite. Then you can divide each side by H. Then you can remove this one. So from here, we can come up with one equation, which is Ts minus T infinite is going to be Q times the length of the thickness of the plane wall L divided by convective heat transfer coefficient H. That's how you determine the temperature difference between the surface and the surrounding fluid. And we have one more equation, that is the temperature difference between Ts and the maximum temperature TO, which is this equation. So if you move this one to the right, left-hand side, we get TO minus TS is going to be Q dot times S squared over 2 times K. So we can come up with these two equations. So whenever you have a plane wall, when one side is insulated and the other side is open, which is very widely used heat transfer problem, then to determine the maximum temperature, to determine the lowest temperature, to determine the surrounding fluid temperature, we can use these two simple equations. Okay? So that's all. That's all. The next slide is a radial system, but heat generation in a radial system is not, the widely used compared to this Cartesian coordinate system. So this is just for your reference. We have a temperature distribution function is given here. And that will be all for one-dimensional steady-state heat conduction with heat generation. So we are going to solve a problem together to learn, how to use these two equations. So this time we have a plane wall whose thickness is only 0.2 meters. So we have a wall and the thickness L is going to be 0.2 meters, and the thermal conductivity K is going to be around 30 watt per meter Kelvin. And it has a volumetric heat generation Q dot. That Q dot is going to be 0.4 megawatt per cubic meters. And one side is insulated. So I'm going to say the left-hand side is insulated. And the other side is exposed to a fluid whose temperature is 92. Then what is the temperature distribution? When you have a plane wall with heat generation, one side is insulated we know because the insulated surface has the maximum temperature. So this point is going to be TO, and we have a TS, and there's a convection outside. So this is going to be T infinite. The temperature distribution is going to look like this. According to what we learned from the previous example, the temperature distribution is going to look like this. Okay? And the temperature of the surrounding fluid is going to be 92 degrees Celsius. And the convection heat transfer coefficient, H, is going to be 400 watt per meter square Kelvin. Now, we want to determine the maximum temperature in the wall. According to the temperature distribution in this problem, we know the maximum temperature is going to be this insulated surface. So we want to determine this T0. How can we do that? We can use these two equations. So let me write them down here. Ts minus T infinite is going to be Q dot times L over K, H. And the other one is going to be T0 minus Ts is going to be Q dot times L squared divided by 2 times K. We know the surrounding fluid temperature is going to be 92 degrees Celsius. And convection heat transfer coefficient is 400 watt per meter square Kelvin. And the length of this, the plane wall is going to be 0.2 meters. And the heat generation is going to be 0.4 megawatt. That sounds too big. So let's say this is not 0.4 megawatt. I'm going to say, where I got this big number? Never mind. So 0.4 megawatt. So this is 400,000 watt per cubic meter. Then you can determine TS. What is TS then? Forty 400,000. 400,000 multiplied by 0.2 divided by 400. Then we get 200 plus 92. So the surface temperature is going to be 292 degrees Celsius. Then we can use the second equation. So from this, we learned the surface temperature is going to be 292 degrees Celsius, and Q dot is going to be 400,000 watt per meter cube, and the length is going to be 0.2 meter square, and thermal conductivity is going to be 30 watt per meter Kelvin. So if you solve this equation, 400,000 multiplied by 0.04, then divide by 30, divide by 2, plus 292. We get 559. So from this, we can determine the temperature at the insulated surface, which is 559 degrees Celsius. So that's how you solve this problem. Any question? So that is everything about one-dimensional steady-state heat generation. Then the last part of this chapter 3 is going to be fin analysis. So let's talk about the fin. Fin is a very widely used, the system usually in a cooling system or heating system too. Like for example, the one of the places where you can see a fin is going to be inside your, the car engine. So if you open the engine room, what is placed, the right in front of your engine? There's a fan, right? And what is behind the fan? You have a fin. Looks like this, right? And radiator. And there's a fan blowing air in this way, right? This is a fin. Then what is this fin? Fin is a extended surface trying to maximize the rate of heat transfer. Then what is the heat transfer in this problem? Is it radiation? No. Is it conduction? No. The air is blowing this way. So the heat transfer phenomenon here is going to be convection between a surface and the surrounding fluid. So it's a convection heat transfer. Then, do you know how to determine convection heat transfer? Yes. The governing equation is going to be Newton's law of cooling. Q is H times A times delta T, temperature difference. So we rely on this equation to determine the rate of heat transfer by convection. So then let's see how we can increase the rate of heat transfer. What are there are many ways to increase the heat transfer. The first one is going to be we can increase the temperature difference. So the simplest way, so think about the radiator in front of your engine. How can we, cool your engine as fast as we can? One simple way is going to be drive to Alaska, right? Because the outside temperature is lower than here, so the rate of heat transfer is going to be much faster than here, right? So what about if you go to Texas? The rate of heat transfer is not going to be as good as here because the outside temperature is higher than here, right? So that means this delta T. Delta T means the temperature of the engine, the surface, minus the temperature of the surrounding air. So if you drive to Alaska, this temperature goes down when T has to remain constant. So this, if the T infinite goes down, delta T goes up. Therefore, Q goes up. Problem solved. So when you want to enhance the engine, the cooling system, you can say to your boss, then we can sell the car in Alaska. That's a good idea. But that's not always happen. We want to sell, our car not just here, but maybe in Texas or in Mexico, anyway, this hot area. Then this increasing delta T may not be the best option. So let's think about, another way. Oh, maybe we can improve this H. How can you improve this H? So there are two different ways. First, you can increase the forced convection. You can increase the air velocity. So you can suggest that, the owner's manual, or if you want to increase the cooling of your engine system, drive faster. Yeah, that's a good way. So if you stay, in a parking lot, if you drive faster, of course, it increases the forced air velocity. So that will increase the H value. Okay, that can be one option. But we want to make sure that the engine is okay when it is in idle in a parking lot, right? Then, is there any other way to increase that H value without, the increasing the velocity? You can change the material from air to liquid. So drive into the river. Then that will increase the cooling system because the H value goes up, right? But that's not a practical option, right? So changing, my point is that, yeah, you can do so technically, but my point is that changing H value, changing delta T may not be a practical option, right? So the only way to enhance this Q value is going to be increase the surface area. So how can we increase the surface area? We want to cool our engine. So if you want to increase the rate of heat transfer from your engine, you can make your engine big, like as big as this classroom. So you're going to, place this giant engine in front of your car and then drive. The cooling is going to be extremely fast because we have a large surface area. But you don't want to do that, right? That's going to be block your sight, right? Not just block your sight. It looks very stupid, right? So one way we can do is we can use extended surface. So instead of flat surface, you can make an extended surface like that. So this is a fin. Okay? So when the original surface area, let's say the original surface area about, the 1 square meter, what is the surface area of this one? Roughly speaking, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Approximately 12 square meters if you make in this shape, assuming that this length is the same as this length, right? And neglect these small areas. Then roughly saying that you can increase the rate of heat transfer by how many times? 12 times. So increasing the surface area is very simple but powerful way to increase the rate of heat transfer. Okay, I get that. Then, what is the problem here? There's one problem. So let's think about just one fin, one single fin. So let's talk about this one single fin. To use this equation, what is the condition? Let's talk about this fin. To use this equation, Q is H times A times delta T, the surface temperature minus the surrounding fluid temperature. So I'm going to say, what is the temperature of your engine? Let's say about 200. Okay, I can do that. 200 degrees Celsius. What is the temperature of the coolant when you're driving? What is the temperature? Let's say about 60, 70. Okay, I'm going to say 70 degrees Celsius. Then, if you want to use that equation, the Newton's law of cooling for this single fin, then can we say area is going to be, let's say the entire area is going to be 1 square meter, 1 square meter. Let's neglect the tip area. So it's going to be 2 times 2 square meters. And H value is forced, the convection by air. So let's say about 20 watt per meter square Kelvin. And what is the temperature of the surrounding, the fluid, which is the coolant, 70 degrees Celsius. What is the temperature of the surface? 200. So can we say this surface temperature is 200 degrees Celsius? Yes or no? Can we say the surface temperature of this fin is 200 degrees Celsius? So you can use this equation to determine the rate of heat transfer from the fin to the surrounding. Am I right or wrong? Not right. Why is that? The base, the engine surface may be 200 degrees Celsius. What about what's going to happen here? So this red is going to be the heat transfer. So this 200 degree, there's a heat transfer from this 200 degrees Celsius going this way. Oh, wait, the surrounding is 70. The surrounding area is 70. So I'm going to go this way. Fine. Oh, the surrounding is 70. So I'm going to go this way. No problem. Then keep moving. Oh, some of them. Oh, I don't want to go this way. The surrounding is 70. So I'm going to go this way. No problem. This way. This way. No problem. Then what's going to happen? So heat is transferred from this fin to the surroundings on the way, the by conduction heat transfer. So what's going to be the temperature at this point? 200? Let's assume that the temperature at this location, my assumption, let's assume that this point is 200 degrees Celsius. Is there heat transfer in this direction? When the temperature of the base is 200, temperature somewhere in the middle is 200. Can there be a heat transfer in this way? What is the second law of thermodynamics? Heat transfers from high temperature to low temperature. If the temperature in the middle of this fin is 200, what is the temperature difference? 0. Is there heat transfer? No. So the temperature, on the way, the inside the fin should be less than 200. So I'm going to say 200 is not possible. It should be 180. Then going this way, 160. Going this way, 120. And, the 100 and 80, etc., etc. So we have a decrease of temperature in the fin direction. So can we say 200? Not anymore. Then should we say 180? No. 160? No. 100? No. Then what is the temperature value here? That is not a fixed temperature. This Ts changes in this way. So can we use this equation? Not anymore. So whenever we have a fin, you cannot use that convection heat transfer equation. So we need to come up with another equation. So that is called fin analysis. That's what we are going to study. Now you see the problem. Why we cannot use this simple and powerful Newton's law of cooling whenever we have a fin, because of the temperature decay inside the fin. So we need to come up with another heat transfer analysis only for a fin. So this is a very unique heat transfer analysis that is called fin equation. One minute, okay. Then what is this fin equation? This fin equation is not very difficult. It is all based on what we studied in thermodynamics and early in heat transfer. So let's talk about a fin in this way. So this is a fin. The base temperature is going to be, let's say, T of base, TB. The surrounding fluid is going to be T infinite. Of course, the base temperature is greater than the surrounding fluid temperature. So we assume that heat transfers this way. So there's a heat transfer this way. And in the meantime, there is a heat transfer to the surroundings. This way, this way. Okay, this way, this way. This way, this way. This way, this way. Then, one thing for sure is the heat transfer near the base to the surrounding is much greater than the heat transfer near the tip. So this way. Why is that? Because let's say the base temperature is 200 degrees Celsius. the surrounding air is 20 degrees Celsius. What is the temperature difference between near the base and the surrounding fluid? A lot. Maybe this one is close to 190. The surrounding is only 20. So the temperature difference is going to be 170. But when you go this way, the temperature of the fin is going to decrease. So the difference in temperature between the fin and the surrounding is going to decrease. Therefore, the heat transfer decreases. Then let's look at a very small volume, this one. So I'm going to look at this very small volume. Okay? Then we have a fin like that. I'm going to say this is a circular fin. If you want to use a rectangular fin, doesn't matter. Then what is the heat transfer direction? So there is a heat transfer from the base to this control volume this way. And what is the heat transfer? Is it conduction, convection, or radiation? The red one. Through this fin. Is there any moving, the fluid? No. That is, through this solid fin. So that's going to be conduction. So this is Q by conduction when X is X. Let's say the thickness of this control volume, this one, I'm going to say this is dx. Then what about, the heat transfer in this way? That's also conduction. Q by conduction. Then, do you think that this conduction heat transfer should be the same as this conduction heat transfer? Are they the same? Not really. Why? Because there is a convection to the side. So there's a heat transfer to the side. So we have a convection heat transfer. Then, because of this energy loss, the conduction heat transfer here should be less than the conduction heat transfer going in. So incoming conduction should be greater than outgoing conduction because there is a outgoing convection. When we talk about conservation of energy principle, Q by conduction X should be the same as Q by convection plus, I'm going to say this is going to be X plus dx. Q by X conduction X plus dx. So incoming heat transfer should be the same as outgoing heat transfer. Okay? Then from this equation, Q by conduction at X should be the same as Q by convection plus Q by outgoing conduction at X plus dx. Then, can we determine this one? How do you determine this incoming conduction heat transfer? By Fourier's law. What is Fourier's law? Minus K times area times dt over dx. dt over dx. That is Fourier's law. That's how we can determine conduction heat transfer goes into this small volume from left to the right. What about this convection? We can use Newton's law of cooling, which is H times area times temperature difference, delta T. What about the convection heat transfer, outgoing conduction heat transfer? This one should be different from this one, right? So can we reuse this one? No. So I'm going to use the first two terms of the Taylor series. So this one is going to be minus Ka dt over dx. Do you know how to, calculate how to determine the second term of the Taylor series? That's simple. This is x direction. So the first derivative of this with respect to x times the distance dx is going to be the second term. So we have d over dx of this one minus Ka dt over dx times the distance, the thickness of this one, dx. Okay? Then, before we solve this problem, we have an area here, and we have an area here. Are they the same or not? The area, this one is going to be for this heat transfer. So that should be the cross-sectional area. So this area for conduction is going to be this area, which is this area. So I'm going to say it's going to be cross-sectional area A of C, A of C, A of C. Then what about this area? This is the area where convection takes place. Is the convection takes place this way? No, to the surroundings. So convection takes place on the side surface. This green is this area. Then I'm gonna say this area is gonna be parameter is this one. P times the thickness dx. Can we do that? Yeah, no problem. Then what about this delta T? This delta T is going to be the temperature difference between the temperature of this small volume and the surrounding fluid T infinite. So this delta T is going to be T minus T infinite. Then let's solve this problem. So this should be the same as this one plus this one. Then one thing in common is going to be this one looks exactly the same as this one. So you can cross them out. Then this equation can be rewritten as H times parameter P, H times P times dx times T minus T infinite is going to be, let's assume that K is constant. Yeah, K can be constant. What about the cross-sectional area? The area changing? No, usually constant. Then these two can come out. So minus Ka and the second order differential equation with respect to x, dt square over dx square times dx. Can cross them out. Then we can move. Oh, my bad. So this is non-negative sign. 0 is here. Then we can divide each term by H times P, like the printer, right? No? Oh, no. I'm sorry. Let's divide by KA. Yeah, it wasn't a printer. Then, and let's move this one to the left hand side. This one also left hand side. Then this equation becomes dt square over dx square is gonna be minus HP, the printer divided by KA, T minus T infinite is gonna be 0. Then this is the governing equation. Can you solve it? Can you solve it? I can. Can you? Looks complicated. I'm not going to solve it. There are genius mathematicians in Pierce Hall. I'm going to call them and let them solve it. And they did. So we are not going to solve this way. We are going to assume theta is T minus T infinite. Then what is the derivative of this theta with respect to x? D theta over dx is going to be dt over dx. What is t infinite over dx? Nothing, because T infinite is going to be the temperature of the surrounding, so that goes away. Let's take another, the derivative with respect to x. Dx square, d theta square, dt square, dx square. So we can replace this one with here d theta square over dx square minus printer divided by Ka, and T minus T infinite is theta. Theta is 0. Now, can you solve it? Yes, we can. Then, this HP over Ka looks too complicated, so I'm going to replace it. I'm going to say M square is HP over Ka. Then that equation becomes d theta square over dx square minus m square. Theta is going to be 0. So this is the governing equation. Can you solve it? Oh, I told you, the people in the mathematics department solved this equation. And the general solution to this one is going to be theta, which is T minus the surrounding temperature, T infinite, is going to be C1, an unknown constant C1 times E2mx. By the way, m is square root of HP over Ka, plus C2, another constant, E2 minus mx. So this is the general solution. But that's not the end. We have two unknowns, C1 and C2. So if you want to determine C1 and C2, how many boundary conditions do we need? One, we have two unknowns, so we need two boundary conditions. Then when we have a fin like that, one boundary condition can be, what is the base temperature? What is the temperature T? T is base temperature TB when X is 0, when X is at the base. Okay, we have that. That's a simple boundary condition. But Can you come up with another boundary condition? Unfortunately, this is the only thing we know. So there's no another boundary condition. So what we can do? We need to create a boundary condition that is called tip condition. What's going to happen at the tip of this fin? Do we know any idea? We don't know. So we are going to do a reasonable guess. So I'm going to assume there are 4 different, the cases. I'm going to assume at the tip of the fin, I think there's a convection. Yeah, that's what happens. I know that. It is the most realistic. At the tip, there should be convection to the surrounding. Then, can we use that? No problem. Then, what is the solution? What is the temperature distribution? What is the temperature T of the fin at a certain location minus T infinite over the base temperature TB minus T infinite. T infinite is the surrounding fluid temperature. What is the temperature distribution? This equation. Do you think that this equation is simple? No. What about the entire heat rate from one single fin? This equation. Looks simple? No. So, even though this tip condition is the most realistic, the solutions look complicated. So let's find another, the possible, the tip condition. One, we can say, I think the tip is insulated. May not exactly reflect the reality, but it is possible. In that case, the temperature distribution is going to be this simple. Nice. And fin heat transfer rate, capital M, which can be found from here at the bottom of the table, hyperbolic tangent, M times L. Okay, that's not bad. Maybe I can say I know the temperature at the tip. Very unlikely. We can suggest that kind of, the boundary condition. So I can say prescribed temperature. Then this is the temperature distribution. Simpler than this one, but still ugly. This is the fin heat transfer rate. Still ugly. Oh, these two are ugly. Let's find the simplest one. I'm going to say the fin is extremely long, so it is almost infinite. Then, what is the temperature distribution? Very simple. What is the fin heat transfer rate? Very simple. So, depending on the tip condition, these are how we calculate the temperature at a certain point in the fin. And this is how we calculate what is the total heat transfer rate from one single fin. So this table is the solution to any fin analysis. In your exam, this table is going to be provided. So depending on the problem statement, you need to determine which is the case of our fin. Then if you are required to determine the temperature at the fin, use these equations. If you are required to determine the heat transfer rate, then you can use these equations. Okay? Any question? That's the theory part. And next week, we are going to study, okay, once we assume that we know how to determine the rate of heat transfer from a single fin, how can we evaluate their performances? That's what we are going to study next Tuesday. And I think we can finish chapter 3 next Tuesday. That means you have a new homework assignment for chapter 3, which is due a week from next Tuesday. And we can start chapter 5 next Tuesday. And hopefully we can finish everything by Thursday, so you can have a second exam before Thanksgiving. If we cannot finish everything by Thursday next week, then we can finish everything by Tuesday the following week. Then you may not be happy about that, but our second exam is going to be Tuesday on the week of Thanksgiving. So it depends on our progress next week. The next week is very important. So don't miss those classes, okay? Any question? That's all. Thank you. See you next week.